Class, welcome back to CSC 143, Introduction to Data Structures in Java. This video is the lecture for week 6. We're studying chapter 12 in the Building Java programs on recursion. And just as a brief reminder for any of those joining you in us in the middle, CSC 142 and 143 are a University of Washington curriculum taught at all Washington State colleges. It's similar to Intro CS classes available nationwide. We use the book Building Java Programs by Stuart Regis and Marty Stepp. We use the 4th edition, although the 3rd edition is fine. You can get that edition online if you'd like. And 143 is really about data structures. So let's take a quick look at what we've looked at so far in data structures. We've reviewed classes, we've looked at inheritance and interfaces, we've looked at array lists, we've looked at Java collections with the list sets and maps, and now we're going to take a look at recursion. So I'm going to do a kind of a combo of the first 4 sections of chapter 12 all together. I'm going to rearrange the order that is presented, so if you're trying to follow along page by page, it's not going to work. I'm just going to give you what I think is a more logical presentation. I'm going to start off with definitions. So the book provides a definition of iterative programming, where it's a programming technique in which you describe actions to be repeated using a loop. And that's fine. That's what we've seen so far. Iterative programming is just the same name that we give to all the programming that you've seen so far. What we're about to introduce is a new type of programming called recursive programming. It's a different way of thinking about problems. It's not a different type of problem. In fact, all problems that can be done iteratively, I think you could probably do recursively, and vice versa. So the book gives a definition of recursive programming as a technique in which you describe actions to be repeated using a method that calls itself. That's a completely accurate description for what it is, but it doesn't really help you much. It doesn't explain why you would want to do it or what the advantages or disadvantages are. So I noticed another definition in Wikipedia. Recursion in computer science is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. And I like this definition better because it gives you a little bit more insight into why it's useful. Okay, so when you have problems that a smaller instance is easier to solve, recursion may be a good way to solve it. I'm going to switch now to trying to show you a visual example of recursion. The book tries to do an introduction where it's saying that if you wanted to figure out what place in line you are, you would ask the next person in front of you, and they would ask the next person in front of them, and so on until you get to the very last person when they would say, oh, well, I'm first in line. And then it would come back and everyone would say, oh, I'm second. Well, that means I'm third, blah, blah, blah. The problem is that no one ever does that, so I don't think it's a very good example. Let's try to show you a visual example that maybe will make a little more sense. So as motivation, I'm actually going to jump ahead into the book to section 12.4 where it talks about fractal graphics. And I'm going to do that because I think for those of you who are visual learners, it might make a little bit more sense. And it's also kind of a cute way to examine recursion. So I still remember when I was a summer intern at Microsoft, one of my fellow summer interns was hogging the copier, and he was just printing out reams and reams of paper. And I was asking him, what are you doing? And he said, oh, I'm making fractals. And I said, well, what's a fractal? And he showed me. So you start with a picture. In this case, it's a balloon. You can take a look at this website for more information about how to make photocopier fractals. And you take the picture and you reduce it. And you reduce it, and then you lay a couple of them out in some order. In this case, he's turned the page a third of a page, 120 degrees each time. And then he's got 3 copies of the clown. I'm not sure if that's a third of the size or half the size, whatever. But you reduce it, and you place 3 of them, and then you take a photocopier image of that. Now you repeat, okay? So you reduce this image, you take 3 of them, you turn them at angles to each other, and you repeat. So we take this, we reduce it, we get 3 of them, and we get farther and farther and farther. This is an example of recursion. And the interesting thing about recursion is that look at the pattern you get as you keep on going farther and farther down. It's really kind of amazing to think that this is the image of a clown. Okay, it keeps on going and going and going. You can imagine how my friend ended up burning through a lot of copier paper doing this. But So one interesting thing about this example is that if I was to give you a problem of coding up this image using clowns, you would probably be pretty lost as to how to do it. Even after having seen what I just described, you would have a very hard time figuring out how to make this image iteratively. Okay, just thinking about it. Okay, I'm going to have a for loops here, and yeah, it's pretty daunting. Whereas recursion is actually a much better way of doing this. Okay, so now we're going to switch to Eclipse and show you an actual program that does this type of imagery. Okay, and the program takes as its input what they call a level. Okay, so a level 0 or 1 image would be just the simple image like this. A level 1 would be like this. A level 2 would be like this. Level 3 would be like this. But I want you to be clear that the way that the program is going to solve the problem in recursion is actually going backwards of the way I did it as a human being with this photocopier. So you would start saying, okay, what I want to produce is a level 3 image. In order to do a level 3 image, I'm going to draw a level 2 image. Whoops, going up. And in order to draw a level 2 image, I'm going to draw a level 1 image. And in order to draw a level 1 image, I'm going to draw a level 0 image. Okay, that's the way the program actually works. So now that I've explained, we're going to go look at this program that does it backwards. Let's go take a look at the code and the execution. So this is a program that comes out of chapter 12.4, I believe, and it's called Sierpinski, Sierpinski triangle. And I'm just going to skip directly to running it and show you what it looks like. So it asks me, what level do I want? So let's start at level 1. So a level 1, it just draws a triangle. Everybody knows how to draw a triangle, right? And this is the sense that the definition was useful. The definition was saying that recursion is a type of programming where it relies on a simpler version of the program. So the simplest version of the program, in this case, is level 1, and it's just drawing a triangle. Let's take a look at what happens when I draw a level 2. Okay, a level 2 means that we've recursed one level. So we drew a triangle. Remember how we did it in the copier? We then reduced it. We put 3 of them on the page, and then we took that picture. Okay, so it's doing the same thing as the photocopier, except in reverse. Okay, let's go to level 3. So for each, before I draw this, I want you to think about this. So what we would do is we would take this figure, we would reduce it, and then we would make 3 copies of it. So this big image here, this triangle with the hole cut out of the middle, that's going to go here. So there's going to be a hole cut out of the middle. It's going to go here. It's a hole cut out of the middle. And it's going to go here. It's going to be a hole cut out of the middle. Okay, so that's level 3. Now let's go to level 4. Again, I want you to think about what is it going to do. It's going to take this whole image. So hard how to describe this. There's 4 holes in the middle. All right, it's going to take this whole image, reduce it, and then it's going to put it here. So it'll be 4 holes, 4 holes, 4 holes. Let's take a look at that. Okay. And we go so on, so on, so on. I'm going to go all the way out to level 8. Okay, so now instead of 4 holes, there's, I can't even count how many holes there's going to be. Let's try level 10. Let's try level 11. Let's try level 12. Let's try 13. Notice how these images are getting slower. 15 and slower. And let's try level 16 and slower. And this is actually a very good point about recursion. One of the downsides of recursion is that recursion takes a lot of memory and takes a lot of time to do all of this. Generally, iterative solutions are going to be faster, but they're oftentimes much harder to figure out. You're going to see that the code to do this is actually very simple. So what is the code? So there's only 2 methods in this program, and this again comes from the book. The first method is just the main method that kind of dries everything. I've set up a drawing panel. I'm prompting for a level. I should say the book is doing it. I threw in a little code to erase the previous drawing, and then we just draw the first figure here by computing these 3 points on the edges. What does the draw figure routine do? Well, again, if it's level 1, let's go back to level 1. If it's level 1, all it does is it just draws a single triangle, okay? If it's not level 1, then we figure out the midpoints. So this is just trying to figure out how to where to place the triangles. Okay, so it's figuring out the midpoint here, here, and here. Okay, and then it's drawing three figures: a figure here, here, and here. Okay, but instead of level 2, it's going to draw a level 1. And what's a level 1? A level 1 is just a triangle. Okay, so let's draw level 2. So it calculated the midpoints, and then it drew a level 1 triangle here, here, and here. Okay, so let's go to level 3. So what it's doing is it starts at level 3, comes in here, and it draws a level 2 figure here, 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 and then it draws a level 1 figure, and then it actually breaks up this figure into 3 triangles, and it draws a level 1 figure here, here, and here. So that's a visual illustration of what recursion is about. And again, it's a good example really only because it shows you that you can come up with things that you really don't know what the quote answer is going to be, and it's very hard to figure out before you get there what the answer is going to be, but recursion can solve it for you. And one of the reasons recursion is interesting is we use it a lot for artificial intelligence, because artificial intelligence these days, pretty much most people agree now, the best way to approach artificial intelligence is not to program in. We used to think that we could program in all the smarts that was necessary to, for example, drive a car. Now most people agree the best thing to do is to design a system which is capable of figuring it out. And then we actually don't know what the rules are to drive a car. We just provide a system that can figure these things out, and then we let it go. Okay, just like in this example, I don't know what this figure is going to look like, but I've designed a system here that can figure it out using some very basic information here. Okay, in this case, how to draw a triangle, and then I let the system figure it out. Now that's a very broad generalization, so don't tell anyone that I told you that's how artificial intelligence really works. But that's a broad generalization of why something like recursion is useful. So we're going to switch to a very simple example from section 12.1 where we're just going to be drawing some stars. But before I do that, I just want to point out the important parts of this recursive method that you'll see as well. So always look for what's the base case. That's how you're going to design recursive code, is figure out what's the base case. When do you stop? What's the simplest problem? Okay. In this case, it's this simple triangle for level 1. And then the other thing you have to figure out is what are the recursive case or cases. In this case, it's for anything more than level 1. You break the figure up into 3 smaller areas, and then you draw the next lower level down on the recursive case within that area. Okay, and it keeps on calling it. So if we start with 4, it's going to call it with 3, call it with 2, call it with 1, and then 1 it ends here. So at this point, we are switching from motivation and kind of inspiration to real mechanics. So I'm going to show you how to do this function called WriteStars, which the book demonstrates in section 12.1. Don't ask why would you want to do this recursively rather than iteratively, because you wouldn't. Okay, it's just a very, very simple example that will help illustrate the process. Okay, so don't think that all recursion is like this, because it's not. All right, so first let's do the iterative solution. Write out n stars in a line. Very, very simple. So we're just going to write out a loop for int I equals 1, and then I is less than or equal to n, I plus plus, and then we just got to do a sys out of a single star, and we're not going to do a println. We're just going to do it like that. And then when we're done with the loop, then we'll do a sys out println. Okay, so that's going to write 5 stars. So if I run this now, there we go, 5 stars. Okay, now let's talk about how to do this iteratively. So let me generate the header and I'll come back. All right, I've generated the recursive version's header, and I've listed out a couple of things to start. So one is I'll list out examples of what each call is going to generate. And I think this is very important in recursion so that you understand what is the difference between each level of recursion and what is the base case. So the base case is when do we stop, okay? And for if you look at this list of calls here, you can see the difference at each level. Obviously, we're just adding 1 star. And we see that when we stop is when we get to level 0, right? And 0, we aren't going to print anything at all. There's actually a carriage return, though. It's a new line. That's important to note. It's a little hard to display here, but when we have 1 star, we're going to print 1 star and then that carriage return. When we have 2 stars, it's 2 stars and then that carriage return. 3 stars, 4 stars, 5 stars. Okay, so we only print 1 carriage return, and that's when we get to level 0. If we just have a level 1, we print 1 star. Okay, so we now know a little bit more. So the base case is when we have n equals 0. Just print return. Okay, so the recursive case is what we want to do is we want to print 1 star and call itself with n minus 1. Okay, so that's my pseudocode. So now I think that's all the pseudocode we need. So let's actually try to write this here. So the base case, we're going to check if n equals 0. We're going to sys out. Recursive case, else we just need to call, we need to print first. So we're going to print 1 star, and then we're going to call itself, right? Stars are with n minus 1. Okay. All right, so now let's go back and modify. Instead of write stars 5, we're going to do write stars r. Okay, let's run that. Okay, so it worked. Let's actually debug this and see what it's doing. Set a breakpoint right here. Debug F11. Okay, so let's take a look at n. We can hover over it, n equals 5. So nope, it's not going to equal 0, so we print 1 star, and then we call write stars n minus 1. Okay, so we are now in it again, and you can see here, this is the actual trace. So we'll come back to this stack trace in just a minute, but you can see that we've entered write stars a second time here. So it's going to print a star, and then it's going to call write stars with n. N should be 4 now, right? So it's going to call write stars with 3. So n is 3. So nope, we're going to print the star, call write stars with 2. Okay, it's going to call write stars with 1. Okay, and you notice that each time we're calling, this call chain is getting longer, right? And finally, okay, so n equals 1, we still got to go 1 more. Finally, we get to n equals 0. All right? Okay, so let's go to n equals 0. We print the carriage return, and then we're going to have to wrap up all, okay, it's not going to show me, but it wrapped up all 5 of those calls because the last thing in the function was to call write stars. So this is actually technically what we call tail recursion, when your recursive call is the last thing in the function. And some languages and compilers, when it sees tail recursion, it can actually convert it to an iterative function because it's just a simple way of doing things. So what did we learn? We learned that there's a base case. We learned that there's a recursive case. The base case is the simplest case. It's very helpful to write down a list of the calls or the list of the different levels so that you can see what happens to each level and what the base case is and what you're supposed to do. And we also talked about what tail recursion is, although that's not really something you need to know. I made a very small modification here and reversed the order of the write stars and the printing. And let's think for a second, what is going to happen here? So what it was doing before is it would print a star and then call write stars to print the rest of them. Now it's going to call write stars and it's gonna call recursively all the way down to level 0. It's gonna print the return, and then it's going to start printing the stars. Okay, and actually, let's do one other thing here. After we call WriteStars, let's just illustrate what this is going to do. So we're going to print that before and afterwards. So this is when it's going to get down to the end. It's going to print their carriage return first, and then it's going to start printing at the return of each. It's going to print the stars. Let's go ahead and debug this again, because I think this is going to be a little bit confusing without the debugger. So we come in with n equals 5. Okay. We are going to see, we're going to call WriteStars 4, which immediately comes in. It calls WriteStar 3, comes in, WriteStars 2, calls WriteStar 1, and where are we now? We are now n equals 0. Okay, finally we're at n equals 0. So first thing we're going to do is we're going to print a carriage return. It's a little bit hard to see, but I think we'll see in a minute once we start, when we start coming back up from this call tree. All right, so we've returned from WriteStars of 0 when n was equal to 1. Okay, we called WriteStars 0. Now we're going to print our first star. You see this blank line here? Okay, so print out the blank line. And now it's going to keep on returning. So now this is where n was 2. And it just printed WriteStars 1. So it's going to print another star, 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 star. And then we come out and we print, this should be on a new line, but it's not, right? Because the carriage returns weren't in the right place. At this point, you're ready to go ahead and start writing some simple recursion problems. So I'm, as usual, using PracticeIt.cs.washington.edu. It's a free site that anyone can go and register on and do problems. And these correspond to the problems in the back of the book, although not all the problems in the back of the book are in PracticeIt in these later chapters. So the problem is star string, and so it's going to create a bunch of stars. And just like in my previous example, it's laid out an example here for 4, 3, 2, 1, and 0. And you can see that instead of printing 1 star and 2 star, 3, 4, 5, it's actually using powers of 2. So 2 to the 0 is 1 star, 2 to the 1 is 2. So it's doubling each time. 1, 2, 4, 8, 16 stars. So it's a little bit different. And so let's, if we recall back to how I was doing the other problem, the main things we need to figure out are the base case and the recursive case. In this problem here, you also have to throw an illegal argument exception if the value passed is less than 0. So we can go ahead and do that. I'm not going to show you all the cases, but I'll at least show you this because I know some of you may not be familiar with this. So if n is less than 0, then we just do a throw new illegal argument exception with some word like bad arg. Okay, now what's the base case? So again, what's the simplest case here? The simplest case is when n is equal to 0. And when n equals 0, we just want to print 1 star, okay? So don't worry about how everything else works. Just worry about the base case. So n equals 0, print 1 star, okay? What's the recursive case? So in all other cases, what are we doing? For 1, we print out twice as many stars as we did for 0. For 2, we print out twice as many stars as we did for 1. Notice if you try to do it like saying, oh, well, we print 2 more, we print 4 more, we print 8 more, that's going to be a lot harder, okay? So you do have to realize that we're actually using powers of 2 here, which mean we're doubling. Okay, so we have to print twice as many as level n minus 1. Okay, what does printing twice as many as level n minus 1 mean? Means what we need to do is call print, call star string on n minus 1, and we also need to call star string n minus 1. Okay, so if we call it and we call it again, that's going to print twice as many as the previous level. So I'm not going to give you the exact code here, but if you put the code in here for if n equals 0, you're going to print 1 star. Here, otherwise, print star string of n minus 1 plus n minus 1. That should probably work for you. Here's another problem. This is problem 12.2, and here we're doing WriteNums, which instead of printing a certain number of stars, actually prints the numbers 1, 2, 3, 4, 5, or 1 through 12, or whatever it might be. So again, the way we analyze this is we look for the base case and the recursive case. This problem again has the illegal argument exception, so you need to put that in for an error case. But what is the base case here? So they've given us 2 examples. Let's write out a couple more examples. Okay, so I've written out the first 5 cases so that you can see what is the base case. The base case is when it's the simplest, and that's when n equals 1. And then we just print 1 by itself. And now what's the recursive case? So for each level, for level 2, all right, we're going to, first we have to do level 1, and then we have to print comma, space, and then level 2. For level 3, we have to print level 2, and then we have to print comma, space, 3. And for level 4, we have to print level 3, and then we have to print comma, space, 4. So those of you who have taken 142 and using building Java programs recognize this as a loop and a half fence post type solution. The first thing you have to do, the half loop, is to print the first number, right? And then after that, what you're going to do is print the rest in reverse order. So you're going to print the comma and then the number, comma and then the number, okay? So this should actually be somewhat familiar. So for the recursive case, we are going to first call WriteNums of n minus 1, then print comma, space, and then let's put n. Okay, so this is the full loop here that we were talking about after printing the half loop here. So I'm not going to show you, I'm not actually going to do the code for you, but if you understand how I've done this type of problem, it shouldn't be a problem to generate this code to get the rest of it. Here's another problem. This one takes a new direction because you have to deal with odd and even numbers differently. So they give you 3 examples here, but I'm going to give you the full first 5 examples. So right squares of 1, I'll give you a hint, that maybe is where you're going to stop, and you just have to print 1. Right squares of 2, they want to see the squares of 1 times 1 and then 2 times 2. So that seems pretty straightforward. Squares of 3, they want to see the squares of 1 times 1, 2 times 2, and 3 times 3. But notice that in order to do 3, you have to print the squares of 3, then comma, space, and then the right squares of 2. Okay, so for squares of 4, we are going to print the squares of 4, but what we're going to do is we're going to print the squares of 3, then on the right side we're going to do comma, space, 16. And similarly, for the squares of 5, it's going to have the squares of 4, but before you print it, you're going to have to print the odd squares. So depending on whether, so the base case is pretty straightforward, but the recursive case depends on whether the number is odd or even. If it's odd, you want to print that square, then comma, space, then call right squares of the next lower number, which will be an even. If it's an even, you want to print the right squares of the lower number, 3. Then after that, you want to print comma, space, the squares of the current number. So I'm not going to show you the code, but the difference here is that you're going to actually, your recursive case now has multiple recursive cases, depending on whether it's odd or even. In this problem, the recursive case is actually doing the same thing each time, but the the base case actually depends on whether the number is going to be odd or even. So if in the case if it's 2, then you're going to have to be printing 2, and if it's 1, you're going to have to print 1. And then you notice that for, well, it keeps on adding the same things, but yeah, it's a little bit more challenging. So I'll give you this one hint on why it's challenging. So if you take a look at the case for 3, well, here, let's start with the base case again. So you notice from 2 to 1, you think, oh, well, it's just adding a star. But from 3 to 2, it's not adding a star, right? So I've told you there's 2 separate base cases here. Then you take a look at going from 3 to 2, and you think, well, wait a second, there's 2 stars here, and there's only 1 star here. So it didn't just add on. But if you take a look at 3 relative to 1, now you see, because these are odd numbers, you need to actually look at the base case for the recursive case for 3 actually has to go to recursive case for 1. Similarly, the recursive case for 4 really needs to go to the recursive case for 2. So 5 has to go to 3, 6 has to go to 4. Okay, so this is really showing different odds and even behavior. This one introduces return values. So far we've just been printing things, so now you're actually going to have to return the values, and in the recursive case you actually have to deal with return values and then multiply by something. This problem introduces not only returns, but returning strings and string concatenation. So you see the base case here. This is just they want you to repeat the string a certain number of times. So they don't show wow1, but you would imagine wow1 is just going to be wow. Wow2 is going to be wow wow. Here hello of 3 is hello hello hello. So the interesting thing about this is they're talking about how to make it efficient. So they're saying if you called foo 500 times, then that's a lot of string concatenations. They don't want you to do that. Yeah, there's a little bit of a trick to cut the number of concatenations in half. I'll let you think about that. But really the most important thing is just understanding how to use strings for this problem. So this is where I'm going to stop this video. This is what I consider the simple recursion problems. The next video I'm going to do is on more advanced recursion problems using recursive backtracking. So let's quickly review what have we learned. So we've learned that recursive programming is about trying to solve a problem that becomes simpler with a smaller version of the problem. So there's always a base case here. And for example, wow 0, when the number is 0, we just print the string. Okay, and then you're going to have a base case and a recursive case. So the recursive case just takes it does some operation at the current level, and then it calls the recursive case with n-1. Doesn't always n-1. It could be n+1. It could be any method really. We just actually looked at a problem where it was n-2, right? But eventually you have to terminate. Eventually you have to terminate. So you've always either got to go downward towards 0 or some small number, or you're going to go upward towards some fixed number. But you got to have some way to terminate. And you're going to be doing something at each level, and then doing something with the previous levels. So we've talked about how some of these recursive problems are just drawing stuff with prints. Some of them are returning numbers. Some of them are returning strings. You can have multiple base cases. You can have multiple recursive cases. So there's lots of different varieties here. But the idea is that recursive problems can sometimes solve problems that are very difficult to kind of get your head around without really going through a lot of code. And that's why artificial intelligence oftentimes uses recursion, because we can't necessarily see how to make the car drive itself. But we can set up a system by which we can drive very simple problems, and then the car can teach itself on how to handle driving more complicated problems. So that's it for this part, and then look forward to another session on more complicated recursive programs.